Good morning, everybody. This morning, in the last installment of my lectures, I would like to talk a little bit more about the general aspects of computing, how we now and in the future try to make use of large, powerful supercomputers in our area. And as you'll see, and many of you know, of course, this is a rapidly developing field. The computer technology is evolving to our advantage. We can exploit this power, and that's the goal of computational astrophysics, to make this power available in these machines, make it available for interesting physics calculations. So first, I want to discuss a bit basically the general challenges involved in running multiphysics, multi-scale simulations that address a high dynamic range in spatial scales and time scales, and this is really where the challenge lies. And then I will talk a little bit more about how do we actually parallelize codes and what are the current technologies that are used, and what does that mean for the future. So the dynamic range challenge is really very severe. If you think about something like, oh, you would like to simulate maybe a black hole in your galaxy to study an interaction of the black hole accretion with this general star formation in a disk. It's called AGN feedback, one of the very fashionable subjects in the field, as you know. Maybe you want to simulate this, then in principle, if you want to address the black hole size and the size of the accretion region around it directly, you're talking about milliparsec scale, so this would be sort of the Schwarzschild radius of the black hole embedded in something of order, say, 10 kpc linear size. So there you go. There you right away have a dynamic range of 10 to the 10 in spatial scales. But even going to star formations, clear if you have a galaxy with 10 to the 12 solar mass then resolving individual stars on the scale of a whole galaxy is a humongous enterprise. This is going to be challenging you with a dynamic range of about 10 to the 12 in mass here. So this is clearly something that is still prohibitive for quite some time also in the future. So you'll have to somehow work around this. And just to illustrate what this dynamic range of 10 to the 10 really means, and I think it's just an abstract number maybe to many of you. Here is a zoom into the Millenium Simulation. This is basically the whole universe, 3 gigaparsecs from left to right. And you can zoom in just by factors of 2, and you do this sort of 8 times here. And then you're down in the cosmic web to a rich galaxy cluster, which you see. And at that scale, this simulation already runs out of steam. And you cannot go really much further than that. So if you imagine then this 3 gigaparsec here is your galactic disk now, and you want to get down to the black hole in the center, that's what you have to do. That's how many factors of 2 you have to do. Right? It just shows you what this really means. If you're naive about this and say, oh, I do this anyway, right? Good luck. So achieving high local resolution, however, this usually means also a high dynamic range in space and time and mass. And to make a few more examples of this, I want to illustrate it with these numbers here. So assume again that we say we want to have a 10 parsec resolution, which is a sort of a canonical goal for the galaxy formation community on large scales, on cosmological scales, and you want to have the same a 10 megaparsec volume, which is maybe the smallest you would hope to get away with in structure formation calculations, even though this is a scale, a box size that will already go nonlinear at low redshift. So this would require about 10 to the 18 cells if you tried this with a uniform mesh, which is then 1 billion times more than a 1,000 cubed run. Which is still a sizable simulation by today's standard, right? 1,000 cubed would be still sizable. So this would be 1 billion times bigger in terms of computation cost. But hey, wait a second, this is not really true. Because if you make the mesh size smaller by a factor of 2, this will also reduce the time step in general by a factor of 2, at least the Courant time step. So that means that if you are improving the linear resolution per linear dimension by, say, a factor of 10, the computation cost really goes up by a factor of 10 cubed times 10, or 10 to the 4, because you get another factor of 10 from the time stepping. So that would mean that if you want to go from your 1,000 cubed calculation to one that has 1,000,000 cubed, you really would increase the computation cost by a factor of 10 to the 12. That's a whole lot, and it's really very sobering consideration. On the other hand, computers keep getting faster. A factor of 100, there's a 0 missing, sorry, a factor of 100 in just factor of 100 in every 10 years. So that means we have to wait 60 years to get this 10 to the 12 power increase. So I hope most of you will still be alive in 60 years. I won't, very likely. So that's not an option either, to wait that long. So, but you know, most of you will know where this is going at. Fortunately, we don't really need, of course, a uniform mesh. We need this high resolution only in a small fraction of the volume. And if that's the case, then we can use adaptive resolution techniques to reduce the computational cost by a huge factor, right? So another example, suppose you want to have this 10 parsec resolution now, say, in the ISM of a galaxy, and you try again to do this for the whole galaxy for a radius of a 200 kpc. In this case, you would need 10 to the 13 cells with a uniform mesh. You want to cover the whole galaxy, a spherical system, say, radius 200 kpc. With this sort of resolution, you would need 10 to the 13 cells. If you only want to cover the disk with that, say, radius of maybe 10 kpc, height maybe a kpc, then you need only 10 to the 8 cells, and that's maybe doable, right? So you see, if you concentrate the resolution where you're really interested in, there you have a chance to address this. This is basically the hope of adaptive resolution techniques. Yeah, so adaptive resolution, spatial resolution is really the way we want to go. So in SPH, we have already seen that the Lagrangian character of SPH automatically provides an adaptive resolution, which is in particular very well suited for gravity-driven structure growth. Here we will start out with a diffuse cloud of gas, or of gas. And as gravity-driven structure growth ensues, these particles will be bunching up, will concentrate actually by very large factors, and then increase the density, for example, in the center of a galaxy by up to a factor of 1 billion or so. And so correspondingly, you have an automatic increase in the spatial resolution just there where the mass goes. And the mass ends up in a very tiny fraction of the volume. So you're ending up only refining spatially a tiny fraction of the volume. So for this class of problems, which is for occurring a lot in our field, SPH is really quite ideal. The one issue one has with this is one needs, of course, to put the particles in the region of interest initially. Then this adaptive resolution with constant mass will automatically guarantee that you maintain this constant mass resolution in your region of interest all the time. So that is quite convenient. But the downside of SPH is that it's actually difficult to change the resolution on the fly during a calculation. So if for whatever reason you then maybe dynamically detect that at somewhere you would like to have still better resolution, then basically you would like to maybe split up the SPH particles. This is something that has also been tried in the field and is at some level doable, but it's a very dicey procedure. Mostly also for two reasons. One is that you have a problem to initialize these new particles. What should really be their initial, say, velocity, temperature, and so on. You have to sample and interpolate this from the neighbors. That will entail some level of error and noise. That's not so problematic, actually, because SPH is anyway relatively noisy. More problematic is that what doesn't really work particularly well in SPH is that if you have particles of different mass in the kernel, then the accuracy gets another hit, basically. And so in general, it's not a good idea to have multiple masses in SPH. At least if you do, at the boundaries, you will not have very trustworthy dynamics. Now, then there is, in Eulerian codes, the modern technique of adaptive mesh refinement. And that is something very powerful. It can be used to selectively increase the resolution in certain regions of space. And there are two basic approaches, algorithmic approaches for doing this, primarily used in the field. That is, one thing goes under the name of patch-based adaptive mesh refinement, and the other is tree-based adaptive mesh refinement. And the patch-based scheme sort of places, as the name suggests, somewhere patches of higher resolution meshes. And these patches, normally they are somehow constructed that, because in typical calculations you will have something like a refinement criterion. So the adaptive mesh refinement tries to do this dynamically on the fly as needed and required by a simulation. So maybe you start out with a uniform mesh in a cosmological calculation, and somewhere a galaxy forms, and you will then place such a refinement on the forming galaxy. And the question is, how do codes automatically detect where to place a refinement? This is, of course, where a lot of the art is doing that. You need to maybe have a criterion that flags certain cells, and in this patch-based scheme you will then have some algorithm that consolidates these flagged cells into a finite number of patches, taking then also, I mean, this will mean, for example, here in the patch-based scheme, that you will always somewhere also refine where it's maybe not really needed in the corners of your patch, for example. But using such patches is relatively easy then for bookkeeping purposes. You can basically write maybe a kind of evolution routine for a given patch, and then reuse that routine all the time, and make this basically like an object in some sense. The other approach is tree-based refinement, and that is more flexible. Here you basically also have kind of a tree similar to the Barnes and Hart-Ock tree, where you say that I can maybe refine even a single cell, replacing it with 8 daughter cells. And that can be repeatedly done, so that you have the freedom to refine any cell by any arbitrary amount you want. In practice, also these schemes will usually employ some kind of cleaning procedure to avoid huge holes and gaps into high resolution region. Yes?
So I'm wondering if using the tree refinement strategy, and then you see the right left bottom part, this big box, and the refinement.
You mean
some refinement grid is
this?
sitting on the top, and this black one.
This one?
Yes.
This
and
here?
There's some boundary because you suddenly jump
from yes.
the first to second level of refinement.
Right. Yeah. So here, right in this picture, you have a jump in resolution by factor 4 in adjacent cells. I think I think Ramsey's actually will not allow this. It will, as far as I know, if I remember this correctly. Is Roman here? Probably not. Or maybe there's some experts in the room, but there are some downsides to this. So some AMR codes, for example, restrict the allowed refinement patterns such that you only are allowed to refine by a factor of 2 for adjacent cells, right? So that will also mean that some of these refinement regions, they are then enlarged a bit. That makes them rounder, topologically nicer, and the boundaries are much better behaved that way. I'm not an expert actually in AMR to the extent that I would know whether this is permissible or not, or whether just good practice suggests this is dangerous. I don't quite know. Yeah, so AMR, and this is another example from an AMR code. Here you see how this would pan out in practice in a 2D calculation. Here is some sort of Rayleigh-Taylor finger, some heavy fluid going down, and then you see that the code has refined this region with a finer mesh in some adaptive fashion. So as I said, this hierarchy of nested grids allows you in principle to achieve an arbitrary dynamic range. And the refinement criteria can be chosen almost arbitrarily. What is problematic a bit here is that if you have a quick motion of a well-resolved region, that obviously requires then a lot of regridding or new generation of meshes. Essentially, in the path, for example, imagine this structure would move here to the lower left corner. Then, in order to not lose the information you have on this high-resolution grid, you somehow would have to ensure that in the path where this is going, the resolution is always increased sort of ahead of the wave in a way, right? So that you don't lose too much of this information. So I think this is a challenge, certainly for AMR grids, that they suffer here also the same issues that we discussed yesterday, the advection problems, that they are also quite apparent if you have this sort of well-resolved things moving with high velocities through space. The accuracy at grid boundaries suffers normally in AMR. That's something that one has to be aware of. Usually they typically go down to actually to first order accuracy at grid boundaries. So there's a, so this is not terrible, but it's not great. I mean, you would ideally like to maintain the same order, right? Now the moving mesh code that I discussed yesterday also has a mesh, and on the other hand, it's also behaving like a Lagrangian technique, right? So it's a quasi-Lagrangian method, and however, you can also here do mesh refinement. This is illustrated here. If you have this Voronoi mesh, you would refine the mesh by actually splitting this one mesh generating point into 2 points. If you do this, and they are basically placed at identical coordinates or very small perturbed coordinates, you do it, then you're actually splitting the cell without changing any other cell. You split it into 2 cells. So this is how you can introduce dynamic refinement, and this procedure is well defined because you can calculate the new volumes of the 2 cells, and then, for example, in the proportion of these volumes, you can subdivide them conserved quantities in the cell, and then you get basically no perturbation in the fluid. You can also remove a point. If you take out this blue dot, what happens then is that actually the volume of this cell is now claimed by the surrounding neighboring cells, as you see here. What you then have to do this on the fly is you have to calculate the new mesh geometry and work out what's the fraction of the volume of this original cell given to each of the neighbors, and with that proportion you have to give the conserved quantities to these neighbors. Now, similar to SPH, this method keeps the mass resolution approximately constant. independent of the clustering state. So this is very similar to what SPH does. But because of this procedure, you now have slightly more freedom. You can dynamically refine and de-refine the mesh. That is similar in spirit to AMR, even though technically it's very different. Also, one other technical difference is that here one uses a mesh that at any given time covers the volume, so tessellates the volume, so there's only really one space filling mesh, while most AMR codes, they use basically a mesh hierarchy. You have a mesh refinement, and on the refined mesh, the evolution is done with high resolution, but then to carry out the evolution of the coarser grid, basically this hole where the refinement is still filled with the coarser grid, okay, where the finely resolved solution is then coarsened to this coarser mesh. So in a sense, you are covering some space multiple times with different resolutions. That's not the case here. And also, the resolution changes now here gradually. So there is actually now a localized error at resolution change boundaries in this scheme, because the resolution simply changed smoothly, and there's no extra error for the adaptive resolution. So the dynamic range that we have in cells or cell sizes, if we spatially refine, reflects itself then usually also directly in the dynamic range in time. And typically, what you'll have is in a typical calculation, in say in structure formation of a galaxy evolution, is that you maybe have this from Greg Bryan, a figure of a cosmic web, again an AMR grid. And then if you work out how many cells you have and what their time steps is, then you end up with a time step hierarchy. Very often this is dealt with in a binary way, that you have a hierarchy of allowed time steps. You calculate, for example, the Courant time step of a cell, and then you put that into a hierarchical sequence of allowed time steps, which differ by factors of 2, right? And they are nested into each other in the time integration, as you'll see in a minute. And typically, in a large cosmological simulation, you will often find a situation where most of your cells will have, say, some large time step. Say, in this case, I suppose 1 million cells are on this large time step. But then there are smaller cells, or hotter, denser cells that are smaller, that will have smaller time steps. And generically, this is sort of a triangular distribution where you have a tail of cells going to small time steps. And the dynamic range in time is then basically the difference between the smallest time step that you need to do for some of the cells and the largest time step that's sufficient for most of the cells. That's generically usually a situation that you have, that there are only a few cells in the tail of the time step distribution, while the bulk has much larger, easier, longer time steps. The question then is, how do you time integrate this? And normally, basically, there are codes that the simple way is that you use a global time step. This is the simple and also the safest way. And Flash has used this. I think it still uses only this. I don't know. I'm not an expert in Flash. Yeah? Ralph is nodding. So Flash is still using a global time step that basically in this sort of situation, if you had this time step distribution, Flash would say, okay, I'm evolving the system on the time step delta t. And that means all the cells. That means I'm doing a step delta t, even if I have an AMR grid, which comes probably from one of the smallest cells. Then all the other cells will also be evolved, every single step with delta t. That's, as I said, it's so-called global time step, where you are dominated by whatever the shortest time step is doing. Right? If that decides to go down by another factor of 2, well, the cost of your simulation will also go up by a factor of 2. So a single cell can cause that behavior. The alternative is to try to exploit so-called individual time stepping, that you somehow achieve that only these 10 cells, for example, that are in the tail of the time step, they are evolved with the time step delta t, and the 100 cells I have in twice the time step are taking twice longer time steps, and so on. So every cell is evolved on its natural time step. That is obviously more efficient, right? Because that means the million cells you have here, they will have to be updated only every 32nd step. And now you can work out, so what do you guess is the saving here, if you between the individual time stepping and the global time stepping? Any guess? So I think what you'll have to do is basically first of all, what's the total particle number? You would have to sum this all up, right? In the global time step, that means to traverse, say, the time of 32 times delta t, in the global time stepping, you would do 32 times a time step with all these cells. And the cost is roughly the cell number times then 32. In the individual time stepping, you would say, okay, this 10 particles I have to do 32 times. These I have to do 16 times, those 8, those 4, those 2, and those 1 times. And so then the saving would be expected to be about a factor 28.4, roughly. So it's not quite 32 because of this distribution in the time steps, right? So that would be the ideal speed up that you could get from individual time stepping. Obviously, this is a strong function of how deep this hierarchy is, right? If the dynamic range in time becomes larger, then very quickly, say it's not just like here, 6, or maybe it's a factor of 1,000 or so, then also the saving is about a factor of 1,000, right? So Flash, with its current technology, will never be able to do a very large dynamic range in time that's exceeding 1,000, right? Yes?
So actually the question is about when you do this AMR, how your computer knows to compute these AMR labels. Because as I know, they usually wait until you calculate the first level of refinement. So all the machine will be assigned to do this.
Mm-hmm.
So then you go to an upper level. But eventually, if you only have few refinement at the very highest levels, then most of CPU are actually waiting.
Yeah. Yes, I mean, you're right. What you're basically saying is, and I can also illustrate this here, if you have an AMR mesh that's refined, or for example, let's say here, maybe some of the coarser or some of the finer meshes, they are much smaller also than the big mesh, and initially maybe there's only one, and there are only a few cells refined, and then the question is basically how do you parallelize that? And similarly here, if I have this time step hierarchy, on the coarse level I have 1 million cells, and maybe I want to run this on a parallel computer with 1,000 cores, so I can maybe do that. But then I have a step with only 10 cells, and that step I also would like to parallelize. Now you apply 1,000 cores to 10 cells. What is the speed up you expect here, right? You will not see 1,000, right? So that is, I'm getting to this. This is in fact a severe problem that which ultimately has to do with the fact that we are bound to, we cannot really calculate this stuff asynchronously, right, in physics. So we have to do the small step first before we can do the next big step. If it wouldn't be a problem if all this work could be sort of decoupled in time, then you could parallelize it. But because we have this bottleneck that there are global synchronization points because of the physics, that we have to complete a previous time step normally before we can start the next, that leads to a situation that some of these things that are in the tail of the distribution in time step, they are extremely hard to parallelize. And because they come up all the time, right? Like every second step in the individual time step integration, every second step will be a step with 10 particles here. That will mean that if you don't parallelize them well, you will be dominated quickly by the cost. In fact, this happens in practice, as I just currently also experience again with run. So In practice, basically what you do in an individual time step integration is sort of something like this, that you have maybe these are your particles or cells, whatever. This is here an example from the Gadget 2 code, but other many codes work like this. Here at a certain time, maybe this is t equal to 0. You have all your particles here. They are all starting basically, they're all synchronous here and require a force calculation at this time. And then, but some of these particles have short time steps, like these red ones, where you see many dots in this time sequence. Then there are others that have much longer time steps, okay? And then as the system integrates this, you will basically have a situation where at any given system time, some of these particles will be synchronous and require, say, a force calculation there. And it looks like this, and then the next time step will look like this. So here you have, for example, 3 particles that are kind of active, that need a force calculation, and the previous step you had 8. Here you have 3, now you have 15. Now you have 3, again 8. Okay. Yeah, this is too primitive. I think I don't have more slides. Anyhow, you get the picture, right? It's trivial enough. We slide this forward in time, and every single system step, there's a different mix of particles that you want to evolve. And that also creates paralyzation challenges, because you basically would like to decompose these set of particles somehow, maybe with spatial domain decomposition, which you might maybe not want to repeat every single time step, such that every step in the sequence is actually balanced also in work. Okay, I'll get to this issue in a minute. Before I do this, however, I want to discuss once more the operator splitting approach to deal with the time integration of multiphysics problems. And we have already seen this twice in my lecture and also in Ralph's lecture, how this is done. And I want to just formalize this a little bit more so that you understand the mathematical basis better for this. So if, for example, we take the Euler equations here, our conservation law, and then on the right-hand side we can have so-called source functions or source terms describing other physics. This can, for example, be radiative cooling, diffusion or chemistry, and things like this. So these are so-called source terms. And normally, as this equation says, you would be forced to now modify all your Riemann solver and Godunov scheme to include these source terms directly, because they are part of the equations. And then each time you add some physics here on the right, you would then again have to go and change your basic fluid solver to account for that directly in every step. That is very cumbersome and also difficult. Fortunately, it's not necessary normally. And to see this, we can consider a general differential equation. For example, we have a time evolution here of this u given by 2 terms here on the right, a and b. Then suppose you can, as I discussed already a little bit, with the Hamiltonian decomposition, the operator splitting there, and also the directional split, suppose we can solve this modified equation where we just drop the b and just consider the evolution under a. And then I say alpha of t is now a function that gives me the evolved state of u starting at u0 just under the action of a. And that equation has the solution e to the ta on u0. So that is an operator equation. A is here the operator that acts on u0. On u0. Similarly, you can solve this equation if you drop a, which is then of course another equation, right? It's just describing the evolution under b. And the solution for this, suppose let's describe this with the function beta, which is then the solution under the evolution of b over some time t, starting from an initial state u0, right? This is what it gives us. And then the conjecture of operator splitting techniques is basically this, that you say the so-called Lie split approximate solution for the full system, that is the original equation, is given by this, that I say I first evolve it under A, and then I evolve whatever comes out of that again under B, right? So you plug in what the evolution of A gave you over a time step h, starting in U0, and whatever comes out of that, you then plug in into the evolution under B, and that is my approximation to what comes out of from the real system here. This is the so-called Lie split. And in operator language, you would then say I'm applying A first and then B. You could also do it the other way around. And a strung split is this here. Here you are symmetrizing the application of these operators. You, for example, first do A for half a step, then B, and A again for half a step. Now the question is, and I've been asked this also yesterday a few times, is this really something you can do, and how accurate is this? Now to check the accuracy, what you can do is you can look at the difference between this, say, Lie split approximation relative to the real evolution U of H, right? And actually, this is this here. You have the Lie split is this application of B, then A, say, or the other way around, and then you have you subtract the evolution under the full system. Okay. Because we understand this, what can we do next? Well, we can do a Taylor expansion, right? So this is obviously pretty much the same as this here. Taylor expand these exponentials. And you find if you work on this, that the linear term actually drops out. And the error then here is something that is proportional to time step delta t or h equality squared. Okay? So to linear order, this is okay. Right? I can do this operator, make this operator split. And this is actually the commutator here between these two operators that you know from quantum physics. So then the leading error term is proportional to h squared. And you can invoke, by invoking in this expansion, the Baker-Campbell-Hausdorff formula that deals with commutators of, or deals with exponential expansions, power series of operators. This is appearing in quantum mechanics. If you use that, you can then show that actually this term is 0 here, drops out in the strung split form. So there the error is only proportional to the delta t cubed. That's why basically these operator splitting techniques are permissible. And so if we then go back to our Euler equation, we can view this really as a system where basically this is maybe the part A and this is the part B. I mean, of course, I can put this on the other side, right, with a minus sign. So you really have that the evolution of the gas itself under the Euler equation, so it's described by this flux divergence, is just one part on the right-hand side of such a generalized differential equation. And so I can, for example, say my alpha evolution is the evolution under the flux divergence, which is the Euler dynamics, and the other is maybe, for example, the evolution under some chemistry. And then for that very same reason, you can now decouple these two processes and time integrate it, for example, in the strung split fashion, which effectively means that you first do, say, a hydro step, ignoring all the extra physics, and then you do the extra physics ignoring the hydrodynamics. And this extra physics might also require much shorter time steps. Then you would call this subcycling, right? You could, for example, subcycling a chemistry part. But this would be mathematically completely fine, and you can actually even formally estimate the error that you make by doing this sort of decoupling. And this strung split is of great help, and in fact, we already saw that twice before, right? I showed you an example for the gravity split in the 3 p.m., where we decoupled the long-range dynamics from the short-range dynamics. And this was one example, and the other was the directional splitting in a Cartesian grid code, which is often done. Now I want to talk a little bit about parallel computing in general and some basic issues there. And one basic issue is what everybody should know about is Amdahl's law. So that basically says the following. Often you have a code, and a code will be a sequence of different stuff that you do, call them A, B, C, D, E, and so on, and they all take a certain amount of time in a serial code. Right? You do maybe calculation A, then you do calculation B, and calculation C. And parallelizing in it traditionally means you speed up each of these steps individually. Maybe you work on A, you make B, in this case, make it 5 times faster, you make A 2 times faster, and so on. And there will always be some fraction of the time, which you cannot make faster. And that's called the residual serial fraction. And this residual serial fraction, however, is a fundamental limit for the speed up that you can achieve. Because if you have a residual fraction f, and the rest is parallelized say by a factor of n, so if you run it on n processes, it's n times faster, then the speed up that you can maximally get is limited from this. For example, if f, the residual fraction is 5%, you cannot get a speed up of more than a factor of 20, no matter how much processes you throw at this problem. Right? Which is kind of clear. The 95% you can hammer down to almost 0 by using more processes. But the 5% that you initially had will always remain. So the residual serial fraction is a fundamental limit for the scalability. So that, for example, means if you want to have a parallel efficiency of, for example, a factor of 1,000, the residual serial fraction must be less than 1,000th of your original of your whole program, which is really very hard. So this shows you why it's really very hard to get right away, why it's very hard to get scalability to such large numbers, because it means that the residual fraction, and many algorithms have a tiny residual serial part, this has to be basically eliminated entirely. Really difficult. And this shows you this graphically that basically the maximum speed up for a given residual fraction is limited. So that also tells you that it doesn't make sense for a certain application or code, once you go into this saturated regime, to throw more processes at the problem. It's pointless. Yeah, and there is a bon mot here from this guy, Tom Gargill. He said, the first 90% of the code accounts for the first 90% of the development time, but the remaining 10% account for the other 90%. And that sort of just says that, once you get down to this residual serial fraction, this is going to be the hard part, which is, where you may spend disproportionately amounts of time and make no progress. The other thing I want to warn you about is, which also many people are unaware of, but is, I think, important to realize, is that there are some things that have to do with issues of floating point accuracy that affect things that you get out from parallel codes. Because in most cases, at least if you use certain algorithmic strategies, parallelization will change the results of simulations. And normally not in sort of a semantically relevant way, but at the binary level, you're not getting out maybe exactly the same numbers. And if you wonder why is that, you have to look at the following. That, of course, on computers we represent floating point numbers in some limited format. For example, a single precision number has this 30-bit representation with a 8-bit exponent or so, and then a mantissa, 24-bit or 23 bits, and then a sign bit here. Then mathematical and that means, this 32 bits means that there are basically 4 billion possible combinations of these bits. And so there are only 4 billion floating point numbers around single precision floating point numbers. And whatever calculation you do, the result will be mapped to one of these 4 billion numbers. Okay, this is a finite space, so this is like a discrete space of numbers that you have, really. And all arithmetic is done with this discrete set of numbers. And basically the result is sort of defined by the IEEE standard, that you first take these two numbers, maybe you add them together. These are two numbers from the set, you add them together. This creates a mathematically correct result, which then has to be mapped to one of the numbers in the set, which is a rounding operation, right? And you normally round to nearest, or and that is what the typical rounding is doing. A consequence of that is that the law of associativity is broken normally. So if you have three numbers and you add, say, B plus C, and then you add A, you will normally, or you're not guaranteed to get the same result, the same number picked out of the set, if you do A plus B first and then C. And this is, I think most of you will be very well aware of that. This is what happens, right? And this breakdown of the law of associativity has severe consequences for parallelization, because, for example, I want to show you this, illustrate this here and with the tree code in a distributed fashion. So here we have our large tree, and okay, in this particular example, the tree is decomposed with the help of a Peano-Hilbert curve, but could also be done differently, doesn't matter. Ultimately, you have 5, say, domains here. These domains have different parts of the full tree. And if you do a force calculation with this, then you, for example, will find that some particle has to walk the tree, and it will then get force contributions from 3 different parts that are mapped to processor 0, 1, and 2. Okay? And each of these processes will calculate some subset of all of the multipole terms that make up the total force, right? In the tree code, the total force is the sum of multiple forces, those that are selected from the tree walk. So these are illustrated here by these circles. Each circle represents one of the multiple forces, meaning for one coordinate, this is the m over r squared. This would be the monopole term for one of the tree nodes. If you sum them all up, then you get the total force. And suppose you run this maybe with 3 processes, and then you get a parallel calculation like this, that the process each calculates a subset of them. The question then is, what is the total force? And for that, you have to add this all together. And the way, for example, the gadget code will do this is that the processor A will add these 6 partial forces together and deliver the total force for these multiples, and also B will deliver this. And this kind of makes sense. You want to also parallelize the additions of these partial forces, right? So the squared boxes are then calculated in this way. If you then go to maybe another situation where you have fewer processors, you will make a different domain decomposition. The set of multiples you have will still be the same. In fact, actually all the circles, they will have exactly the same value because it's the same coordinate and the same multiple moment. But now processor 0 adds up this set and processor 1 adds up this set. So you get 2 numbers A prime and B prime. And because of this breakdown of the law of associativity, the sum now of A plus B plus C will not be the same as the sum of A prime plus B prime. Even though mathematically everything's fine, right? But you now have round off that spoils the binary invariance of this parallel algorithm. Now, what's the consequence of such round-off errors in collisionist systems? Because such systems are typically chaotic, actually, small perturbations, especially in the nonlinear regime, small perturbations are actually amplified over time. So what this means is that even this is the sort of butterfly effect. You know, if you have even a round-off perturbation, initially this perturbation will stay small, but will still grow exponentially. So 2 nonlinear orbits will start to diverge exponentially from each other. At some point, the force errors can change discontinuously in a tree code, because you can trigger with this deviation that one of the decisions on whether a tree node is open or not is changed. At that point, you get a drastic glitch in the orbit calculation, so these orbits now start to even diverge more. And and basically it's already changes in the number of processes is enough to trigger this. And even changing the compiler settings can be enough to trigger this, because then for very aggressive compiler optimizations, you are allowing the compiler also sometimes to change the order of arithmetic operations. Mathematically still valid, but you can then get different round-offs. So in a nutshell, what this basically means is ultimately that is you cannot expect a convergence of collisionless simulations parallelized with MPI with such algorithms like the ones used in Gadget on a particle-by-particle basis. The origin is for why this is spoiled is ultimately because of such round-off effects, which seem so innocent. And that also means that basically an initial particle orbit is relatively meaningless. The collective statistical properties of a system, however, are not allowed to change through such a thing. So that does not behave chaotically. So I just wanted to make you aware of this problem. Now let me discuss the issues of parallelization a bit more. What is it really that limits us in parallelizing calculations? Well, the most important thing is certainly, which comes first in my list, is incomplete parallelization. So if the residual part in an application program, residual serial part, that's present, then that limits the theoretical speed up that you can achieve. That's the Amdahl's law. That is a very common thing, that you still have incomplete parallelization. The parallelization itself, however, creates certain kind of overhead. You maybe have the need for non-trivial communication algorithms. Those then increase the computational cost. The bookkeeping code that is required to whatever work out how many data you have to send and get, etc., etc. This is causing extra calculations. That is an overhead that sometimes can become very hefty. Then the communication times itself. If you have a network of computers, you need to send data between them. That will take a certain amount of time. On very modern machines, this is actually often negligible because they have often very good networks with high bandwidth. What's more likely to burn you are so-called wait times. These are caused by workload imbalances, where if the parallelization does not balance the work that has to be done by different computing cores, then one of the compute cores will finish first, and then it will idly wait until the slowest one is also done very often, because there might be a synchronization point. And actually these wait times, in my codes, this is usually the dominant thing, which limits the scalability, is the incomplete workload balance. And I will discuss this later a bit more, why this is so difficult to do this perfectly well. When you are asked to write a computer time proposal, you will then ask by the computer centers to provide scaling plots of some kind. And one can distinguish between two regimes. One is called strong scaling. That basically means, and that's the hardest demand that you can put on a code. That basically says, oh, let me keep the problem size fixed. And now you change the number of processors or compute cores you use. And if you double the number of cores, you would like to see double in speed. So the wall clock time to a solution should go down by a factor of 2. That's the ideal strong scaling. That is very hard to achieve for things like the Amdahl's law. Weak scaling, however, means when you increase the number of CPUs, you also increase the problem size. And then this is often more relevant in practice, and it's much easier to achieve weak scaling. You can convince yourself. So basically, you're circumventing part of the restriction that the Amdahl's law poses by using weak scaling. And then here is an example for this. This is a old test I once made for a cosmological simulation with the Gadget 2 code. You know, this is really pathetically small by today's standard, 256 cubed. This was on an ancient machine, IBM Power 4. And here is a strong scaling result, where basically you see that as the number of CPUs is increased, the time for a time step taken in seconds is going down as kind of expected, proportional to 1 over the number of CPUs. And this is here on another, this is at redshift 0, and this is at redshift 50. So here the dark matter was not very clustered. This is the simple part. Here it's almost perfect. Here it's more strongly clustered. You see already that the scalability now starts to become poorer here at the end in the clustered state. You would in principle expect to lie on the dotted line, but you're almost a factor of 2 already here above it. It's always good to plot this in log. It doesn't look so bad, but here you have already a factor of 2 loss almost, right? This is, however, the strong scaling, another figure from the old Gadget paper, where I tried to use the code for a small galaxy, a small problem, a galaxy collision. And here in this shaded squares, this block basically is the total CPU time that's used, and the different shaded parts give different parts of the code. And what is particularly relevant is the white part here in this squared region, because that white part measures the time spent in waiting idly for communications. So this is basically caused by workload imbalance, losses. And if you then run this in serial, there is no white part. You don't communicate at all. So this is basically the intrinsic cost of the calculation. And then if you go to 2 processes, you start to see sometimes one of them is finished earlier. It waits for the other processes. So you have a certain fraction of the time that's available time that's lost due to that, etc. And this keeps growing in this sequence of figures. And that's why basically the strong scaling here is not particularly good. Right? So it's getting faster, but at the end almost not much anymore. I mean, you expect here maybe a speed up still of about 10%, and it's slightly below that. So it's and running out of steam in terms of scalability. And I want to show you why it's somewhat hard to get around these workload imbalances. Because, for example, in this particular algorithm, what the tree code does is it does the force calculation in 2 parts. It does first work on its own particles, and some of the particles need information from other domains, and then they will be sent to these other domains, and these other domains deliver this information in terms of the partial forces for these particles from these other domains. But since this is sort of symmetric, you then, when you send this information, you're also getting such information from other processes, and you doing a service for them and calculating tree forces for imported particles also. And at the end of the step, you send those results back. So basically, there are these 2 phases in the calculation. And what the domain decomposition will do is it will try to make this sum of these 2. This is the elapsed time for all the work that needs to be done. Make this equal for all processes. Then you have a work balance, right? So this is sort of the design that the code tries to achieve this. And suppose it does that almost perfectly, like this. Yeah, you're really happy with this because you have, for example, 8 cores here, and then the work is subdivided like this, that it's almost the same. There are only small little fluctuations here, which is then illustrated by this orange wait time. So you have one process which is number 6, which takes longest, and the others finish slightly earlier, but not by much. And so the lost time is not large here. But so far so good, and that is sort of working in the code. But what actually happens now is somewhat much nastier. So we have this situation. What really happens, of course, this here. Because in the middle, we need to exchange information with the other processors now. And that acts as a synchronization barrier effectively. So then we have one processor, the number 4, which takes this amount of time, and then all the others have to wait until this guy is finished, so you can exchange the information, and then everybody runs again on his work. And then in the end, when you finished with the second part, you have the same story again. Now CPU 7 is finished first, and it waits for the others. Now, even though you balance the total work like this, because you have in the middle synchronization barrier, you get huge imbalances nevertheless. All of this orange stuff is now lost time. And basically, this is really hard to get rid of, right? And so this is sort of a real situation in Gadget 2. Actually, on top of this, you have maybe the gray stuff is now the actual communication time, right? So you have here you can start the communication, then you have some actual times, and so there's quite a bit of loss. And there are ways where you can try to avoid this with asynchronous communication. This is also hard because, for example, I mean, you would want a message to be sent asynchronously. If you entertain this idea, I tell you it's also not so easy. For example, here, suppose you have a situation where A and B needs to exchange some data, and then you would like to do this asynchronously so that they don't have to wait for each other, right? So that basically would, for example, say B at this point puts some message into send buffer, and then A, when it's done, finally here picks it up. Okay, that should work, you would think. But actually, often what happens is, if this message is large, what happens is normally, or many MPI libraries maybe have improved, this is system dependent. What will happen in many systems is this here, that maybe B, yes, puts this into a send buffer, flags this, then when A wants to pick it up, it still needs the cooperation of B. So it will not do anything until the next time B calls an MPI function. So you will actually wait until B is in the MPI library, and this can happen. So this is quite common that this happens. So you then have a wait after all. And then it turns out that this is actually worse than the synchronous case. If you had programmed it like this, that B waits until A is ready, you would have just this wait time, which in this case is shorter than this. So you see, this is just one example that tells you that there are no golden bullets for this problem, right? So you can use a better domain decomposition. That's really what we have to do. We have to domain decompose the problem better to make the workload imbalance smaller. Here is an example. Suppose you have a galactic disk like this, and you can then do a domain decomposition for parallel calculation. So Gadget 1 did something like this, an orthogonal recursive bisection. So for example, you get this sort of domains. The colored regions are now mapped to different processors, and you see maybe you have made a cut first here, and then you cut there, and etc. So you make various cuts, typically orthogonal to each other, and you see that these domains will have rather different shapes, and in particular, the green domain, for example, and the violet one and so on, they have access to the center of the galaxy. These other domains, the red one, doesn't. So in the red one, there are no particles with short time bins, for example. That's also a problem, right? It doesn't have particles. It doesn't have a uniform mix of the dynamical states of the particles. The red domain has only outer parts of the disk, and then there are other domains that have parts in the inner disk. So this is not so good. Here is what you get if you do a Peano-Hilbert-like domain decomposition. This looks a little bit better, in the sense that, better, I'm not sure. I mean, the domains have a much more complex shape, but at least sort of there is a tendency now that because of the adaptive nature of this, that the centra where the density is higher is chopped off into smaller things, and more of the process have access to it. But this is, if you really want to distribute the work better, you basically have to do something more aggressive, something like this, that you say, oh, okay, maybe I should create many more domains than I have processors, then they're all individually smaller, and then I hand them out to the process in a second step to balance their work. And so you can achieve that, for example, the red processor now gets pieces from all over the place, and so it gets then a fair representative mixture of the dynamical states of the particles and hence of the time bins. And with this decomposition, you then have a chance that all the processes have sort of an equivalent part of the calculation problem. And this is sort of what is done in the Gadget 3 code, that when you have 4 processes, you're not chopping off the space filling curve in just 4 pieces, but in many pieces, and then they are recombined to achieve a better workload balance. And that's, for example, on a scaling test, you see this here, that then this creates a better scalability to large processor numbers because of exactly this effect. Okay, so this is a weak scaling plot, for example, for the repo code that shows, you can scale this up to 10,000 cores or so relatively well, but depending on the problem size, you eventually will run out of steam here as well. So this is a constant challenge to improve this further. So I'm now finished with this first half of the morning lecture. Are there any questions about this stuff before proceed? Yes?
So you said that the paralyzation can change your results.
Yeah.
Does that also mean that if you run the same code and the same number of cores on a normal cluster, that might give you different results because cores finish differently, and then the final reduction, for example, of the forces get done in a different way?
This will not be the case with an MPI code, but can be the case with OpenMP. Because, as we'll see now, I discussed this later, these reduction operations, what he means is, say, summing up a bunch of numbers. And in MPI, these operations will be deterministic. And so if you rerun it, you get exactly the same result. With OpenMP, depending, again, on implementation of OpenMP, but normally it uses threads, and it can be that then the threads execute this in different order depending on which thread arrives first somewhere, for example. So the OpenMP can be more problematic in this case, even that it's not repeatable. And secondly, what also is an interesting thing is depending on the MPI library use. I just said that MPI is deterministic. This is true. However, if you are placing MPI tasks differently onto shared memory boxes, for example, suppose you have an 8-core machine and you want to run with 64 processors, then you would use normally 8 nodes of the machine, and every node would get 8 MPI tasks. Okay? And now a global reduction, whatever MPI all reduce or so, depending on the MPI library, most MPI libraries will then do first a summation on the shared memory machines first, and then communicate this back and sum the 8 ones up. If you, however, place the 64 MPI tasks on 64 nodes separately, then there is no shared memory summation to begin with. And then the order in which the stuff is summed up will also be different. And it turns out that then your MPI code, depending on how you place it on the machine, will give you different results. But if you do the same placement, it gives you the same results. So the global reductions are always very dangerous. They are usually affected by round-off. So I see no more questions. Then we go to the last part. So here I want to